Where'd your two classmates go? Or ironically here the first. Oh. All right, any questions before we get started? And so, of course, just a reminder, right, today's our last lecture, so I think we'll get through chapter 9 today, we'll see. And then I gave you all your labs already, right, for today. So basically today's lab will be chapter 9, so a titration, and we'll talk a little bit of the theory of the titration, and then you'll do it. And so that means next Wednesday is exam day. And we will also have a quick lab final, like I mentioned, and checkout. So checkout will be part of your final. And again, shouldn't stress about the lab final or anything. Right.
So would Monday just be used for preparing?
Yeah, so I'll do a review on Monday, so come with questions. We can do whatever practice problems. I'll probably try to go through the exam and like do sample problems or like similar-ish problems, something like that. That's my plan for Monday. Cool. So let's finish chapter 9 so then we can leave Monday for review. And so chapter 9 is all about acids and bases. And so just some general properties of acids. And you probably are aware of this. So, right, you probably have eaten some acids in your life. So lemons or orange. And so acids tend to taste sour. And like we've seen in lab, they can also dissolve many metals. So we saw that with our acid and the magnesium. Of course, it can neutralize bases. We've also kind of seen this in our lab and our worksheet practices. So I'll just write an example. And so we've seen this, and we've called it a double displacement reaction. So of course, just making our salt and water, everything would be aqueous here, liquid. And so we can say, right, this is the same thing as a double displacement that results in water, aka a neutralization reaction. And again, I think we've seen that before. We're just kind of re-emphasizing that. And then we'll play with some litmus paper potentially, or we have. And so it just changes blue litmus paper to red. Although personally, I just prefer the universal indicator. And here's, of course, our acetic acid example that we mentioned yesterday. So again, our weak acid, this is an organic acid. We should point out the group that makes it an organic acid. So all organic acids would have this carboxylic acid group. And so that's just this funny looking thing with the carbon with the double bond and then the alcohol on the other carbon. So that whole thing is carboxylic acid. And so this is just a list of common acids. You probably see a lot of acids in your daily life without realizing it. Hydrochloric acid is also the acid in your stomach. And hydrochloric can be used for metal cleaning or ore refining, some sort of food preparation. Sulfuric acid, this is found in your automobile batteries, so that's in there. It's used in some fertilizer manufacturing or explosives. You can also do electroplating. Nitric acid, so more fertilizer and explosives, and glue production. So acetic acid, so we mentioned, right, that's vinegar, so obviously used in food preservation. Citric acid, so this is the powder that we have in lab, or one of the powders, one of the white powders. And so this one is actually used like to make candy a lot, and we actually like, usually when you buy citric acid for lab, it's cheapest to get it like from the candy distributors. You buy a huge bag in bulk. Otherwise, like the lab citric acid is more expensive. And obviously food grade is a better quality. And then carbonic acid. So of course this is just the acid formed with carbon dioxide and water. So that dissolving, so of course that's going to be in carbonated beverages and also small amounts in the ocean, so everything's in equilibrium. So it's a little bit of carbonic acid. And then HF, so this is used for metal cleaning and a lot of glass etching, and probably also like chip production would use HF. And then phosphoric acid, so this is used in like fertilizers, but also they usually put a little bit in like soda. It's a beverage preservation as well, so small amounts of that. Used a lot in like buffers, so it mentions biological buffers, so that's a common component, especially with it being a triprotic acid. So triprotic just means 3 hydrogens. And so here's the organic acid. So we mentioned, again, this carboxylic acid group. You could recognize that and recognize you have an organic acid. Here's just different examples, your fruit acids. And so only the H in this carboxylic acid group is considered acidic. And all that means is this is where the action is happening. So this is where the hydrogen either comes on or off. So this is the hydrogen that makes it acidic. And so switching to bases, so bases tend to taste bitter. I don't know if anybody ever got their mouth washed out with soap. They still do that.
Happened to my brother once, by my grandma.
Nice, yeah, that's old school.
I was growing up right in the transition from bar soap to liquid soap too, so we got double boat.
So I'm sure you got that nice bitter taste, or maybe some of you will try that on your kids. And of course, right, bases also feel slippery, so you know that with soap. And of course, bases neutralize acids. So we've seen that in lab. And then they change red litmus paper to blue. But again, I like the universal indicator paper better. And so common bases, we've seen some of these. So sodium hydroxide, you can use this in like soap manufacturing, which if we ever wanted to do like a soap club day, we should do that. Anybody want to make soap? I had one student that was like super gung-ho in my 200 level series, and then I don't think anybody else shared that excitement, so we never did a soap day since there wasn't enough like coordination, excitement. Felt kind of bad. And then potassium hydroxide, so same thing, you can use it as well as a base in soap production, so that's just lye. They're all of it just a proper chemical, and can use in other things, so battery, processing, different electroplating. Sodium bicarbonate, so that's baking soda, and is used as an acid. Sodium carbonate is a water softener and is also used in glass soap manufacturing. And then of course ammonia is used as a fertilizer, more explosives, and synthetic fiber production. And so now this is introducing the hydronium ion. And all this is saying is, so often we just shorthand, like for instance, if we take HCl and we show the dissociation, we often just write it like H+. But all this is saying is this wouldn't actually exist in solution. So you can't just have like naked proton, and so it would just get picked up by a molecule of water. So really what's going on as it dissociates, so water is going to pick up the hydrogen, and so that's what's really leading to our dissociation, and then that makes our hydronium ion. And so again, key takeaway is that H plus is the same thing as hydronium, and often chemists use this interchangeably, but again, just realize you don't have this truly floating around in water. It's really hydronium. And so again, like it mentions, we just use it interchangeably with H+. We don't often draw out the whole hydronium. And so now let's look at the definitions of our acids and bases. And we'll mainly focus on the Arrhenius, and I'll at least touch on the Lewis. And so we'll look at the three main ones and kind of go through them. So if we start with the Arrhenius theory, it says that acids produce H+ ions in solution. And so that makes sense. That's kind of what we've seen so far. So we see that with hydrochloric acid, again, disassociating to give us H+ and chloride ions. And that means that bases produce hydroxide ions. Again, we've seen that with our bases. So sodium hydroxide dissociates, again, to make sodium plus hydroxide. So that's a base. And so, of course, acid-base reactions, they combine to make water. And so we've seen that. Again, our double displacement, very simple neutralization reaction. So hydrochloric acid plus sodium hydroxide gives us our salt plus water. And so the problem with this, and we can recognize this one, is it doesn't explain ammonia. So we've seen ammonia, we know it's a base, but it doesn't, if we just look at ammonia, NH3, right, there's no hydroxide ions there. So it doesn't tell us how it actually makes a basic solution. And it doesn't tell us how some of these ionic compounds, like sodium carbonate or sodium oxide, they also make basic solutions even though they don't have hydroxide ions. So it doesn't explain everything. And it doesn't explain why CO2 makes carbonic acid and why it makes acidic solutions. And it doesn't explain other acid-base reactions that take place outside of our aqueous solution. And so then they needed a new theory to try to solve that. And so now this gives us the Bronsted-Lowry acid-base theory. And so it's slightly different definition. So now they're saying that any reaction that transfers a proton from one molecule to the other is classified as an acid-base reaction, irregardless of whether there's hydroxide. And so that means an acid is going to be an H+ ion donor, and a base is now just defined as an H+ ion acceptor. And so now this does help us explain ammonia. If we look, so we'll start with water plus ammonia. And then so ammonia has those 2 electrons, right? Don't forget, we can draw this over here. So thinking back to our Lewis dot structure. And so this means it has these 2 electrons. These 2 electrons can pick up a hydrogen. So anytime we see a species with 2 electrons, right, it wants an H+, so it's considered nucleophilic. And so what it's going to do is it's going to come over to this water. Let me redraw this a little better. It's going to attack the hydrogen. These electrons go back to the oxygen. And so that gives us ammonium. Oops, sorry. So there's our ammonium cation. And then leaving us with our hydroxide ion. And so now we can label all these species. And so looking at this, so this is going to be our acid, right? So we said an acid is anything that is donating a proton. And so looking at this reaction, because we'll later learn that water could act as an acid or a base. But in this case, it's giving up a proton. So it's starting off as an acid. Ammonia then, by this definition, is going to be a base. And so kind of our hint is that it has, again, those lone pairs. So that means it's going to be able to pick up that proton. And so yes, it's a proton acceptor. So that makes it our base. And so after our base picks up our proton, now it's considered our conjugate acid. So notice, right, it's our new base species plus our H. So let's label this, so conjugate acid. And again, we can remember it's the acid, it has more protons on it now. And then compared to our conjugate base, where compared to how it was before, it lost a a proton. So conjugate base. So Bronsted-Lowry acids, again, Bronsted-Lowry acids are H+ ion donors. And so we can see that same thing play out here. So it works for our previous definition. So that's the other thing. So this definition still encompasses, right, our Arrhenius theory. So anything that was an Arrhenius acid is a Bronsted-Lowry acid. And so again, right, this is an Arrhenius acid, and we can see how water is acting as our base. And so this time it's accepting the hydrogen and becoming our conjugate acid, leaving our chloride as our conjugate base, since it was previously our acid. And so here's again ammonia, so proving that it's a Bronsted-Lowry base by being an H+ ion acceptor. And so what's kind of nice about this is it's supposed to help us understand the equilibrium better, so we can just write out another example. And so we could look at acetic acid. So starting with the carboxylic acid group, and then acetic acid just has 2 carbons in it, I believe. And so we can then add water as our base. So water can act as our base, draw our equilibrium. So now we're drawing our weak acid, showing that we can draw some electron action. So again, lone pairs on the oxygen. I'm going to pluck off this hydrogen. Draw our electrons. So of course, oxygen got all those electrons. And so what species is this called? Our try again. Because it was our acid. Yeah, so now it's our conjugate base, since it was deprotonated. And so water was acting, yeah, as our base. Yep, so then our H3O is our conjugate acid. Okay, questions so far? And so like we've seen, the original base picks up the proton and then becomes the conjugate acid. And then our original acid becomes our conjugate base. And then of course we can just write this again. So just keep going. And so every reactant and product then becomes a conjugate pair. And so a conjugate pair, all it's really saying is that there's one hydrogen difference between the two. And so if we look at that, if we have, right, this acid-base pair, we have ammonia and ammonium. And so all that we did was, in this case, right, add an H. So there's your acid-base pair. Of course, your base is always going to have less protons than your acid. So again, you're just comparing 2 species. And then if we look at this, so again, water is acting as our acid here, since we're removing a hydrogen, and then it's becoming hydroxide to be our conjugate base. And so now, what about this example? Is this an appropriate conjugate pair, first of all? Yeah, no. So what's wrong with it? What do you mean water and water? But then, so does that make it a conjugate base pair? Because what was the conjugate base pair definition? Because, right, we're not reacting these two. Right, we're not reacting ammonia and ammonium right now. What are we showing?
Okay, so then it's not a proper transfer of a single hydrogen.
Yeah, so
It's a two hydrogen difference.
yeah, it's two hydrogens, so watch out for this, because you might see this on an exam or something where it tries to trick you. And so hydroxide and water, right, that's an appropriate acid-base pair, where this is, right, your conjugate base, this is your acid, and then you can have, right, water and hydronium, so that's another acid-base pair. But exactly, you have to watch out for any time you might get tried to trick by this two hydrogen difference. Or if you're writing it out, make sure you're writing out just the one hydrogen difference. Because sometimes people see like hydroxide and then just write down hydronium as a acid pair. But yeah, it has to be a one hydrogen difference. All right, that's a little repetitive. And so let's skip to the example. And so just go ahead and try to figure it out on your own for a second. Ask your partner. And so just take a look at both of them, rewrite them out. So which one's your acid, which one's your base. And then of course from there, right, which one's your conjugate acid, so it should have gained a proton. Your conjugate base should have lost something, lost a proton. So do we have thoughts for the first one? Are we still looking at it?
So I thought the H2SO4 was the acid, with the H2O being the base, and the HSO4 was the conjugate base, with the H3O being the conjugate acid. But you're calling it all.
So this looks good. Is this what other people got? So I see some nods. So, right, first good start is you have to identify your acid and your base initially, which could be tricky with water. But, looking at this, it's like probably your acid, since you have a lot of protons on it. It's also sulfuric acid, if you can recognize that. But then, of course, right, you look at your hint and you see, well, who's given up your proton? And so it's going to be this species. So, yeah, that is your acid. And then making it your conjugate base. And then your water, of course, in this case, accepting it. So it becomes a base, making your conjugate acid. How did B go? So what was water in this case? An acid, a base? Acid. So it's an acid since it gave up a proton. And so what does that make this species? Our base. And then carbonic acid becomes what? So conjugate acid, and then leaving hydroxide as our conjugate base. Excellent. Seems like you guys did well on that one. And so like we kind of touched on, the difference between a strong acid and a weak acid or base has, again, nothing to do with how harmful it is, but rather whether it disassociates or not. And so strong acid completely disassociates, while a weak acid, only a small percent is ionized. And so same thing, a strong base is a strong electrolyte, and again produces a complete ionization through disassociation, versus a weak base is again going to be a weak electrolyte. So ammonia would be a common example that you would encounter. And so some general trends in acidity. So the stronger an acid is at accepting a proton, the weaker the conjugate base is at accepting a proton. And so what does that mean? And so part of this has to do with the whole disassociation issue. So if we look at hydrochloric acid, so this is a strong acid, and so the stronger it is at donating a proton, so meaning in hydrochloric acid's case, right, it fully disassociates, so it's pretty good at donating a proton. And you can quantify this better, but again, we're just talking more broadly right now. And so we're saying then, so this is going to be our base species, right? This is our conjugate acid. And so it says the weaker the conjugate base is at accepting a proton. And so what this is saying, right, so again, this is our conjugate base. So because this is so great at donating, this makes this a weaker base. And in the hydrochloric acid base, this is so weak of a base that it's not a base. And what I mean by, right, it's not a base, is because in HCl, if it was a base, right, it would reform hydrochloric acid in solution. So it would take this, pluck off a hydrogen, and make HCl and leave hydroxide. But it does not do that. since again, HCl is a strong acid. And so what happens if we compare this to another acid? Let me just write it somewhere else. And so this explains why HF is a weak acid. Also gives us some safety tips. So same thing. And so now this is considered, right, a weaker base. So again, going back to what this says, the stronger an acid is at donating a proton. Well, actually, HF isn't that great at donating a proton, right? So it's a weak acid. It's in equilibrium. So hence it goes back and forth. And so because of that back and forth action, this is saying, right, so this is our conjugate base. And it's actually saying, yes, fluoride can act as a base. And so this is where the danger can occur if you're doing some reaction and you're making fluoride ions. Well, if you're doing that in water, what that's going to do is, of course, make some HF. So then you reform your acid, and then you make hydroxide. So this is now proving that fluoride is a base. So definition of a base makes hydroxide. There's your hydroxide. And we made acid. And so again, that tells us that HF is a weaker base, but therefore its conjugate base then is better. Since it's the opposite, right? Stronger the acid, the weaker the base. So then weaker acid, stronger base. And what kind of helps you with that trend is this chart here. And you have your acid and then your conjugate base on the other side. And this is increasing strength. So all these are going to be your strong acids: perchloric, sulfuric, hydrogen iodide, hydrogen bromide, hydrogen chloride, and nitric. So these are strong acids. Let's highlight that. So our strong acids. And again, the key there is they undergo complete acid ionization, so they point that out for you. And then that means, though, that their conjugate bases, so all their conjugate bases are on the opposite side. And so look, if we look at this chart, so increasing base strength is at the bottom. So down at the top is like no base strength. And so that's what it's saying is, right, nitrates, chlorides, bromides, iodides, all these ions in solution are neutral. Meaning they're not going to be like this fluoride where it was able to react with water and make some sort of acid. That's what we're saying here. And so below this nitric acid, then we can have, right, some equilibrium back and forth. So hydrogen sulfate can lose our proton, become sulfate, etc. Right? These all have equilibrium. So our carbonic acid versus hydrogen carbonate, hydrogen sulfide, right? The trend just continues until we get down to water and hydroxide, and then the trend ends there. And so going back to other general trends, so higher the oxidation number, the stronger the acid tends to be. So just comparing your sulfuric versus sulfurous acid. So the ic has the more oxygen ending, and so stronger acid. So same thing, nitric versus nitrous acid. So nitric is a stronger acid. Usually I don't really see people using sulfurous or nitrous acid on a daily basis. I'm not really sure what their applications would be. And then cation is a stronger acid than a neutral molecule. And then a neutral molecule is a stronger acid than an anion. And so a base would be opposite. And this might seem confusing, but if we look at it, it should be kind of make a lot of sense. So a cation is a stronger acid, and so think of this, right? Our cations are going to be acids. So, right, ammonium, that's also considered an acidic species, especially compared to the neutral. So, right, it has more protons. That's all that's saying. And then bases, right, tend to be anions. So if you're going to have a base, it will be an anion like fluoride, obviously hydroxide. So that kind of helps you navigate what the heck they're saying there too. So this chart is useful. If I remember, should probably print you out a reference copy. So I'll probably try to do that while you're in lab. Let's see. I don't remember how much in detail we need to go. And so we'll at least look at this, kind of appreciate it. And so back to our equilibrium expression. Do we vaguely remember our equilibrium expression, at least just kind of writing that? I'll at least rewrite the basic formula, because we had like A plus little b, gives you a reaction C, big C, plus little d, right? And then it was like concentration of C to the power of C times D to this coefficient of D, right, over the concentration of B to the coefficient of B times concentration A, coefficient A. Bailey, remember that? It was our equilibrium constant expression.
So the little letters are coefficients?
Yeah, so these are all the coefficients from your balanced equation. And so this is kind of related then, and we kind of have to think about what it's saying and write this in terms of our acids. And so now our acid expression, so Ka, so we just have, right, our strong acid, we have Ha, right, disassociates to give you H plus chloride, or sorry, I shouldn't use chloride, plus A minus. And so that gives you your expression. So your Ka then just ends up being concentration of hydronium over concentration of conjugate base over Ha. And so now looking at this, anytime you have a strong acid, well, we're saying it's all going to fully go towards the right. And so this means that our Ka then is going to be large, so favoring our product. So again, just kind of relating back to our equilibrium constant that we talked about before. And so this means we have 6 strong acids. And so I would probably write that down or note that, or again, highlight that same information that's here, but you may want to note that. So again, your 6 strong acids, hydrochloric, hydrobromic, hydroiodic. So that follows with your halogens, just not including fluorine, and then nitric, perchloric, and sulfuric. And so then weak acids, so again, if we were to look at this expression for a weak acid, right, they do not fully dissociate. So then there's going to be some amount of HA still there, still right together. And so that means that their Ka then is going to be less than 1. So that's how you can identify you have a weak acid. And so again, we've seen some common examples: acetic acid, carbonic acid, formic acid, any organic acid.
Okay, just remind, if we have time, can you do one of the math, like, all the way out on one of these? Just that way I can cross it. Like, actually plug in numbers on like one of the acids and how it turns out.
Depends. Yeah, we could do some of that, but, or we could do it in lab. Yeah, or we can come back to it. So blah, blah, blah. So the farther the equilibrium position lies towards the product, the stronger the acid or base. And so looking at this, so this is another good chart. And so again, we're looking at just our equilibrium constant, so Ka. So notice, right, these are all small numbers, less than 1. And so if we look at this down, they get weaker as we go down. And pKa is related to Ka. So pKa is equal to the negative log of Ka. This might be useful. I need to look at your exam, honestly, and see how much of this chapter I go into as well. So again, the larger the Ka value, the stronger the acid. Notice pKa is the opposite though. So the larger the pKa value, the weaker the acid. And this is more just fun for your information. And if you were to take organic chemistry, you would care a lot about pKa's, but we won't go too much further. And so water is beautiful. Can't emphasize that enough. And so water is pretty cool. And so it's also known as amphoteric. And other substances can be amphoteric. And amphoteric means that it just acts as an acid or a base. And if that's true, there have to be some ions present. And so back when they were trying to figure out the whole pH scale and all these ions, they kind of determined this. And so they had some sort of device to measure how many ions they had in solution. And this was pretty cool. And so they found that for water, so just plain water, neutral water, and this is how they got to pH 7. But they found that the concentrations of hydronium and hydroxide were equal in water, and they were both equal to 1 times 10 to the negative 7 molarity. So that's kind of cool. And so this led us to this expression. And so all this is saying is that these two concentrations always have to, at least the product always has to equal to the same number. So it's 1 times 10 to the negative 14. So now this is giving us a clue to why the pH scale is the scale that it's at. So this is super useful. And so you may want to write this down or highlight this. But your concentration of hydronium ions times your concentration of hydroxide have to equal Kw, which is just 1 times 10 to the negative 14. And so this is only valid at 25 degrees Celsius. It does deviate slightly, but for our purposes, right, we're always going to be at 25 degrees Celsius. And so as...
Just go for a second, I think the second half of that.
And then all this is saying is that they are inversely related, so as one increases, then the other must decrease so that they stay proportional. Good? And so acid-base solutions contain hydronium and hydroxide ions. If it's neutral, they have equal solutions or equal concentrations. Acidic solutions have more hydronium than hydroxide, so again, that kind of makes sense. And basic solutions have a larger hydroxide concentration than hydronium. So see if you can calculate the hydroxide concentration then for each of these solutions, and then tell me whether it's acid or base or neutral.
So would you plug the H3O in to a previous equation?
Yeah. So what did, right, because we had the expression, so we were given, so hydronium times hydroxide equals 1 times 10 to the negative 14th, right? And so we can plug our hydronium in and then solve for hydroxide. So what do we get for A? Let me pull up my calculator.
So then it's that equation times the hydroxide equals Kw.
Yeah, hydronium times hydroxide concentration equals Kw.
So we just leave the hydroxide, just the variable the way it is.
Right, since that's what we're trying to solve for is hydroxide. So,
Okay.
so then, yeah, you would take 1 times 10 to the negative 14 divided by your hydronium. So what do we get for A?
You would divide them by the 7.5 times 10.
1 times 10 to the negative 14 divided by your acid.
Okay. So it is just that.
Silly question, 7.5, you don't have to put the times.
I just use a little e. So I would
You
use
don't
it,
have to use times, E.
because if you do times e, you start telling it something different. So it could mess up like order of operations potentially. Because if it's e, it sees them together. If it's times e, it becomes separate in the calculator's mind. Yeah.
got, 1.33, times 10 to the negative 10 power.
Excellent. And so then, does this mean that it's an acid or a base?
What was the answer?
1.33 times 10 to the negative 10 power.
That's what I got when I put in calculating it wrong.
So it depends on like how you're doing things and whether it works out or not. But I would not,
It would be a basic because,
wait, try again.
is it basic?
No.
So it isn't basic, 'cause it's not, and it isn't larger than the, H3O.
It'd be acidic, right, because the H3O is larger than the OH negative?
Exactly, right? So we have to look, so this one's less negative. So then, yeah, it's gonna be acidic. So don't let those negative exponents throw you off. So what do we get for B? Oh, I got people.
I got, I'll just say, I got 6.67. Because I forgot.
6.67
To the negative 6 power.
to the negative 6. Is that what other people got?
So that would be basic then, right? Because it's larger than the H3O.
Yeah, it should be basic. I'm just double checking. Did people get that same number? Oh, now we did? Okay, excellent. Calculator misfires. So yeah, thanks everybody got that. And so you said basic. So that looks good. And then what about C? We need to do math for C.
What would make something neutral?
You tell me.
Would it be like it's the same, or can't speak. The H3O and the OH be the same? Oh, that's funny. I got, you basically got 1 times 10 to the negative 7.
So then what does that tell us?
That's neutral. I mean, it means it's neutral.
Yeah, neutral.
It'll just be water, right?
Yeah. As long as it's neutral water.
Good drink, this says water.
And so measuring acidity, and so this is going to be your next useful formula, as we often express it as pH, and pH is just the negative log of the hydronium concentration. And so if we go back to, let's just do A for instance. So if we type in negative log of H plus, so 7.5 times 10 to the negative fifth, then we get a pH of 4, and so that's less than 7, so that's another way of telling us that solution was acidic. And so it's kind of useful, lots of different relationships you can find. And then this is just a general chart of your pHs. So stomach acid is, of course, super acidic, right, 1 to 3. So that's why they always say if you throw up to rinse your mouth out so you don't have that acid just sitting on your teeth. And then limes, lemons, so of course that's super acidic. And going back to your teeth enamel, you probably don't want to, like, you know, suck on a lemon and destroy your teeth enamel. What do you have there?
My favorite pasta.
Lemon.
What's true lemon?
It's, it's basically crystallized lemon. It has actual acid in it.
So like a bunch of citric acid type powder? And
Just a bunch of citric acid. My mom uses it in her tea sometimes. It's really good.
that's funny.
So, like the stomach acid, isn't that the reason they tell you if you're ever like out of balance to like take a tablespoon of like apple cider vinegar or whatever, because it has the same acidity or pH as your stomach acid.
Yeah, well, people say all sorts of things, and I'm not sure what's best. Although that's an interesting one, and I kind of like that theory to like rebalance your stomach with a little acid.
Well, yeah, because fried food and all that stuff, all those oils are mostly bases, so after eating fried foods and all those stuff, you can actually reduce the pH or increase the pH in your stomach to the point where it's no longer digesting as well.
Yeah. Yeah, because that's the argument of like maybe not using so much antacids, or like why the alkaline water may not actually be as effective. Because yeah, your stomach is acidic, so it just gets neutralized. So.
They say that they think that actually might be the reason that all these food allergies are becoming so popular now.
Because of.
Because your stomach acid just is getting unbalanced, and so therefore your stomach doesn't break things down as well.
So then.
On top of that, with the increase in antibiotics, it kills all the probiotics and stuff inside your intestines, so you don't
Yeah.
break it down all the way.
No, the antibiotics screwing up your gut bacteria.
Well, that's the funny part. They most of the actual remedies, what they give you, like medication for like what's it called, lactose intolerance and the gluten intolerance is actually just a daily probiotic and a acid, stomach acid balancer. That's mostly what they give you.
Yeah.
It's interesting.
Yeah, we
pH
definitely.
pH is a little important.
Yeah, and we like don't, you know, we still don't know enough about the body chemistry, which is so interesting. Because, you know, people go on like the alkaline water kick, but it's like it could be making you worse. And,
Oh, they're 9.5.
yeah, or like any sort of alkaline water.
Have you heard about the one, like one of the first ever, I guess, experiments regarding digestion? It was, this guy was fighting this war, and he got shot by a cannonball or something like that, leaving a big hole in his stomach. And so a scientist basically strapped this poor dude down and lowered bits of food into the gaping cavity in his stomach, see how it would digest. And apparently it was excruciating, can't speak, excruciatingly painful from the one dude.
I would assume so.
You think so, but then again, it was during like the one where they still gave like, I don't know. It was the olden days, the really olden days, like power to weight days.
So did he survive at all? Like.
Probably not. I don't remember. I think he did. I'm not sure how, cause yeah.
I mean, technically, if you're doing it in a controlled environment, you can keep it without the acids going into your internal, because that's mostly what stomach fluids do, is it actually eats away most of your internal organs to leave out.
That's pleasant.
Yeah, I don't think the one scientist dude cared that much
Yeah.
regarding
Probably
mutation.
not.
He was like, oh, so let's see what bread does. He loads bread in, and it was, yeah, very weird episode.
In terms of pH, where do you think pineapple would land on the chart?
It's probably there with like limes and lemons. You can ask Google. So Google says 3.2 to 4 for the pineapple, so as bad. Yeah, soft drinks, fruits are pretty acidic. Beer's not so bad. Argument for drinking beer, no.
Human blood, that sounds.
And of course, human blood, right, that's a buffer, so that's kept at a pretty tight range, so all your chemical reactions can go at the appropriate rates.
A common beverage is. Ever served in Transylvania?
I mean, it has a good pH. All right, so pH of less than 7 is acidic, pH of greater than 7 is basic, and of course 7 is neutral. If we know the pH, we can also go back and get the hydroxide or hydronium concentration and, well, also hydroxide. But the formula is hydronium concentration equals 10 to the power of negative pH. So that's just reversing, right, this log expression. But there's it written if you need help doing that. And so their pH scale, of course, it goes up by 10, so it's logarithmic, and then it goes from 0 to 14, so that goes back to that kW water constant, so that's why it's that scale. All right, so see if you can calculate your pH from these two.
So which formula should we use? Or would give them like two?
Yeah, so you might need both of them.
I have an answer for A.
What do we think?
3.74.
Is that what other people got?
I used the first equation that was shown.
So what was the equation that you used?
pH equals negative log and the H3O inside of it.
So did everybody get this? So we just had to plug this in. So we were given the hydronium, so then plugging it in, and you want to make sure you do it. Sometimes calculators can somehow end up in like the wrong base or something weird, especially if you're using like a different sort of calculator. You have questions on this, Emma? questions? Calculator not working. If you have something way different and you just plugged it in, just double check your calculator, and I can get a calculator or something that we have in lab. And then try the second one in the meantime if you haven't already. And what's the other formula we might need to help us?
I was actually gonna ask if I could see that again, because I wrote it down.
I'll rewrite it. So hydroxide times hydronium, 1 times 10 to the negative 14.
Oh, that one, I was hoping to, that one works.
Which one did you want?
It was, I can't really describe it, it was like the same one, it was on the same slide that the pH equals negative log was.
Mm.
It was a lower equation, but it could have been, example oriented, I guess. This one works.
Can you go through on my calculator how to do those? A and B?
So A, so negative log of 1.8 times 10 to the negative 4th. And if you need further help, I can come look at people's calculators individually, either now or in lab.
Oh, it's a calculator.
It could be though, like.
Okay, I got that. Okay.
That is my warning, is it could be a calculator issue.
I appreciate that, but my calculator's just fine. Might be the operator.
And I'll give people another minute, and then I'll type this one out.
I didn't get a whole number, well, I got a whole number, but not just that.
So did you solve for hydronium concentration first? Let's see, here what you got.
Oh, oh shoot, I didn't, okay, never mind.
Do you have pH?
I got the H3O, I didn't get the pH necessarily.
Okay, what'd you get for H3O though?
I got, 7.69 times 10 to the negative 13th power.
That sounds about right. I'll go through the math. And so I'm just doing a sanity check in my head as well, trying to like multiply the two together and see if they're on the right order of magnitude. So 1 times 10 to the negative 14 divided by our hydroxide. And so I agree with your answer. I'd probably have rounded it to like 7.7 or keep the 6.9 on there, but
And then we just times those two together to get the pH, right?
no, then you take this, right, and then plug this answer into, yeah, this formula.
If we're doing sig figs, I got.
Oh, okay.
Negative log. And so 12.1 or so for your pH.
So for this stuff, do we still do sig figs or no? Is it more like just rounding it out for pH wise or what?
So this, the pH is kind of weird for the sig fig. It follows different rules. So here we have two, so I messed up myself actually. So we have two sig figs, and then so you want to keep that many decimals to the right. So if you have 2, then you report your pH 2 after,
Oh,
which is weird, yeah.
gotta change the rules.
And so I probably won't be as strict for the sig figs for the log ones, just because it gets confusing, because they're like adding, we'll call it like adding sig figs, but I won't be too strict on the rounding. All right. So POH is just another way of expressing our pH. So it has the opposite scale. And if we look, we could also solve for it. So our POH is just the negative log of our hydroxide concentration, which you might expect. And so comparatively, so this is a pH scale on top. Notice your POH scale is the opposite. So if something is acidic on the POH scale, it's 14. Yeah.
Could you go slightly up?
So this is, it's pretty much repeating the hydronium concentration formula, just with hydroxide. And this is really kind of the key relationship is this one. And so it's re-derived from the KW expression, but this is probably more useful and a little bit easier. Just the pH plus POH has to equal 14. This is the derivation of it, so you can tell that it came from the KW expression, but for our purposes, right, we don't need to worry about it. Although it's not that difficult. We just take the log of both sides, so the negative log of this gives us 14. The negative log of each of these just translates out to pH plus POH, right? This is our pH expression. This is just POH, so even though it looks kind of nasty, it's not too bad. But again, this is our key takeaway. That's useful. And so now we have a bunch of relationships, right, to get back to one another. So this and this are kind of our two useful ones. And then, of course, right, our pH, pH equaling the negative log of hydronium, or H plus, right? These, either 2 or 3 expressions are really key. So this is a takeaway before you freak out. So pH plus POH equals 14, so write that down. All right, so we're okay with this one?
I have it written down.
I won't say okay.
We'll do more practices later. All right, so rest of the chapter, so buffer solutions, we won't go too much into this. So what we need to know is buffer solutions resist changes in pH when either an acid or base is added to the solution. And so buffers have to contain their weak acid and their conjugate base, or their weak base and conjugate acid. And so one key takeaway is we might want to know how to at least make a buffer roughly. And so what I mean by that is if we have acetic acid here, and we'll write it out. So our vinegar. So this is going to be, right, our weak acid component. And then, well, let's figure out what it would be its appropriate conjugate base. So what's the conjugate base of this weak acid? What's the difference? What's just our simple, right, acid conjugate base relationship?
Good.
Well, what was the difference between them? There is one key difference.
It would be missing a hydrogen,
Yeah, so it'd be missing a hydrogen.
which would be the one that's paired with that O, right?
Yeah, so that one. So let's first just take that off. And so, right, this would then be our conjugate base. And so notice, all this is saying is then we just need an appropriate conjugate base salt. And what I mean by that is, right, this is our acetate. And so we could pair this with any other ion, right, as long as it's neutral. So we could go with potassium acetate, right, sodium acetate, and they would just have, right, a little counter ion to this. And this is something that you can buy. So with this, right, sodium acetate. And so if you wanted to make a buffer, then you would order some sodium acetate to go with your acetic acid. And again, right, you can recognize, oh yeah, there's my acetate structure. And so again, other buffer systems, it mentions your blood again, where it has some carbonic acid and hydrogen carbonate ions as well. So that's a buffer system. And so then, of course, you can make it, so mixing your weak acid and your conjugate base. And so this is a little wordy, but it's just Le Chatelier's principle. And so just like we were looking at before, right, your buffer is just going to be pushed in either direction, so depending on what you're adding. So looking at this system, so we have our base plus our acetic acid gives us water and acetate. So all it's saying is if we were to add acetate, right, or more sodium acetate, we'd be adding products, right? So then it would shift it back to the left, making more acetic acid. Does that make sense from Le Chatelier's principle and lab? And then same thing, right? If you add acetic acid, you're adding reactants, and then it's going to increase, right, our water and sodium acetate production, and then reestablish equilibrium. Make sense? Yes, no? Questionable? Question mark? And we could do the same thing, right? So think about sodium hydroxide. You add a base into there. That forces, right, the neutralization. So there it is, forcing it right again by Le Chatelier's principle. So it's going to, if we add more reactants, right, it needs to make more products to compensate for that. But then, of course, it buffers out and tries to resist the change in pH. And so all this is saying is, right, your buffer solution. So now we're looking at the case of adding an acid to our sodium acetate. So they just flipped the equation here, essentially. So acid plus conjugate acid gives us acetic acid plus salt. And again, same thing. All we're emphasizing is that the acid's going to be neutralized by your base part. So in this case, your sodium acetate. That does your neutralization reaction, right? But then this can also go back, reform your acetate, and so, right, that's how your buffer, again, resists the change. And so this, again, just kind of goes through that your buffer either neutralizes your acid or base, depending on what it's being added, right? So if you're adding a base, it reacts with your acid part. You add an acid, it acts with your base part, and then equilibrium, go back and forth, resist the change. And so for our purposes, we'll just focus on using this Henderson-Hasselbalch equation. And so all this is saying, if we want to find the pH then of a buffer solution, we can determine our concentration of our base. so AKA, and so let's go back to this system. Sorry, rewriting it from before. So our acetate, I've forgotten what I've written. So this is our acetate, AKA our base. So we could figure out, right, what our molar concentration of acetate was, AKA, right, sodium acetate or whatever base we picked, whatever salt, right, conjugate base salt, also known as A-, like we've seen before. And then over our acid, right, so then this is just acid, or HA, AKA our acetic acid in this system. And then we could look up the pKa of an acid, or it would be provided, like for this weak acid system. And then you would take the log of, again, the concentration. And so this would be concentration, and usually in molarity for that. Questions? And so the last little bit is classifying the salts as acidic, basic, or neutral, which we've kind of touched on. So it depends on all this, right? So what we were saying, the strong acid, the strong base, right, in this chart. And so now let's go through this. And so we'll go through what the word says and then kind of dissect it so that it makes sense. And so the first case is for neutral salts. And let's just read through the words and then we'll dissect it. So it says, if the salt cation is a counter ion of a strong base. Okay, let's just stop there. So counter ion of a strong base. So basically, can we pair it with hydroxide? Because that's usually who it's paired with. Okay, so salt cation is counter ion of a strong base. Check. That's true for sodium, right? Let's continue. And the anion is the conjugate base of a strong acid, right? So conjugate base of a strong acid. So that brings us to chloride. So chloride came from HCl, but we said HCl, right, fully disassociates. It can't go back. So, right, we already established chloride is neutral. Then it says neither ion reacts with water to affect the pH. So that's all we're saying is they're both from a strong acid and a strong base. So equilibrium lies all the way to the right. So in this case, right, it's sodium plus hydroxide. So hydroxide in this case is not going to reform either, or sodium, right? Sodium can't reform the base or anything. It's not going to act as an acid, so it's going to be neutral. So let's, and sometimes I like to draw out this sort of analysis, and so I'll redraw it for sodium chloride here. Right, so I look at my sodium, and well, my sodium came from sodium hydroxide, so that means that sodium is neutral, okay? And then chloride came from HCl. Again, it's strong, so that means that my chloride is neutral. Makes sense so far? And so if we do that for, so let's do calcium nitrate. And so where does calcium come from? What base? What base is it related to? just even TAC, right, hydroxide, how can you pair hydroxide with it?
Wouldn't it just be CAH or HCA? No.
Because it's just talking about, right, calcium hydroxide. So if we can make a strong base with it, so yes, calcium pairs, right, with hydroxide to make calcium hydroxide. So this is going to be a strong base, but that means that calcium is neutral then. And then where does nitrate come from? What? So, right, nitrate has to be paired with some sort of hydrogens to give us an acid. So what acid is it? What acid has nitrate in it? Yeah, nitric acid. And then so is nitric acid a strong acid, weak acid? So it's strong. So if it's strong, right, it's fully disassociated, so that means that nitrate then itself is neutral. So it's not going to go back and reform acid. So that nitrate salt is neutral. And so, right, calcium's neutral, nitrate's neutral, so then overall, right, our salt is neutral. And so let's do that analysis for KBr as well. And so eventually this should feel kind of repetitive. So once you establish whether an anion or cation is neutral or acidic, basic, then, right, it'll always be that way. So that kind of helps you. So what base does potassium come from? Yeah. So potassium hydroxide, right, that's a strong base. So that tells us that potassium's neutral. And then what acid did Br come from? Bromine. Yeah. So hydrogen. Yeah, the only hint for you is that it's an ionic compound, so you have to know it like fully disassociates, because that just follows our normal ones, unfortunately. Because they listed all the strong acids, but the strong bases are just like all your alkali metals, alkaline earth, right? Those are going to be your strong bases. So then, does that make bromine, right, neutral, acidic, basic? Right, it came from hydrogen bromide, so what kind of an acid was that? So strong, so then we know bromine, yeah, it's neutral. So then overall, neutral. So then looking at the rest of this, so now if we look at the next situation, so it says, so the salt cation is a counter ion of a strong base. Okay, so we have the same situation, so it looks like it's going to be a neutral cation salt. But then the anion is the conjugate base of a weak acid. Then the cation is neutral and the anion is basic. So it'll be basic. And so we can go through that analysis. Yep, so sodium fluoride. So what do you know about sodium? Acidic, basic, neutral. Where is it from? So it's a metal. What's it in its base form when it makes a base? So sodium itself would be neutral, yeah. So it comes from sodium hydroxide, so that's a strong base. So yes, sodium is neutral. And then if we look at fluorine, though, what acid is fluorine from? Yeah, so HF, hydrofluoric. But then is it a strong or a weak acid? So it's weak, yeah. So even though it messes you up, it's still just a weak acid by dissociation. And so if we look at that, so let's write out that expression again. And so again, equilibrium expression tells us,
So the acid would be, then that means the conjugate base would be strong, right?
yeah.
So therefore it means it's fluorine that has base for strong base.
Well, not a strong base, but like a stronger base than chloride, yeah.
It's base lead.
Yes. So then we make HF plus hydroxide. So then, yeah, fluorine is basic, which makes sodium fluoride overall basic. So then we can repeat this. So calcium, and anyone recognize what this one is? It's on your sheet.
Okay, it was C2,
H3O2.
acetate.
Yeah. And so what do we know about acetate? You might already be able to tell something. So let's start with calcium. So what do we know about calcium? Acidic, basic, neutral? We've gone through it.
Yeah, that was calcium hydroxide, and it was neutral.
Yes, so this makes calcium neutral. And so we established this was acetate. And what did acetate come from? We talked about acetate like 5 minutes ago.
Acetic acid.
Yeah, so acetate comes from acetic acid.
Strong acid, right?
Well,
No, it was weak acid.
yeah.
For some reason, I mixed up acetic and citric.
Although citric is also a weak acid. It's another organic, should also be weak. And so that means, right, our acetate can react with water to reform our acetic acid and making hydroxide, so the definition of a base. So then we can say, right, acetate is basic then. which makes this calcium acetate overall basic. And this would be an appropriate salt to use for our acetic acid acetate buffer, so calcium acetate would be another choice. We can skip this one, getting. And then our last situation of the three is if you have a salt cation that is a conjugate acid of a weak base, okay, and the anion is a conjugate base of a weak acid, then the cation is acidic and the anion is pH neutral. However, kind of a hint is we'll only see either ammonium or like ammonium-based, basically acids, or right, for salts here. So let's go through ammonium chloride, but then think about other examples. So ammonium chloride, right? Ammonium comes from our base, so we could write, yeah, ammonia plus water. So it gives us ammonium plus hydroxide, but again, it's weak. So that means, right, this ammonium can react with water to give back a proton, reform ammonia, and then make acid, though. So there's our acid. So now this explains why this is acidic. So acidic. So chlorine, or chloride, we already said that was neutral from HCl. And so again, right, cations tend to be acidic, so you're probably not going to have a basic cation. And so like other examples then of acidic salts. This is one that I think actually comes up later on some example. Oops, kind of draw it funny. Oh. But all this is it's another derivative, right, of ammonia. Sorry, going crazy. Where's my pen? All right, so this is just from this compound. So instead of it being ammonia with 3 hydrogens, I just stuck a methyl group on there. So fun trivia, anyone recognize this molecule? What it is? Or you might know it from if you watch some TV.
Something acid. Damn close.
It's methylamine. You guys from Breaking Bad?
Oh,
This is like super highly illegal now, thanks to Breaking Bad as well.
great.
Yeah, because that's the one where they did the train heist episode on, where they stole the liquid. Yeah.
Watch the show, don't look at me.
Yeah, it's getting I guess it's getting too old now. Can't use it. Pop culture reference.
Yeah, I've seen it. I love that show. We talk about so many chemicals.
All right, so that's that. The other last little bit, but we won't worry about that in this class, is so like, you know, what happens if you have where like ammonium fluoride, for instance, right? Ammonium is acidic and fluoride is basic, so how do you know what the salt is? And so with there you have to compare the Ka strength versus the Kb strength, but that's kind of sometimes tricky, so we won't do this in this class, but you can at least appreciate how you would figure that out. So again, comparing your Ka of your acid versus your Kb of your conjugate base and see which one's larger. All right, let's do this practice real quick. So determine, oh, and then last bit, so aluminum is weird. So aluminum, usually you just consider it acidic. So aluminum, again, one of your metals, so any of your charged metals, so metals tend to be acidic. So if you see that aluminum, it's an acidic solution. All right, let's try to do this practice, and we'll talk about a little bit of titration before we do a titration. And we'll ignore this last example too.
You said aluminum, those metals are acidic,
Yeah,
they form weak bases.
they form acidic solutions, so form hydronium ions in solution. Nachos, so. Don't get me excited for nachos. Do we have an answer for strontium chloride? So neutral, right? Strontium came from strontium hydroxide, so that's neutral. Chlorine, of course, from HCl, so that's neutral. What about B? So acidic, so that was from our special aluminum case. So metal. And it tends to look at the higher oxidation states, so like aluminum, gallium would probably be similar, but aluminum is a little special. What about C? I try to give you a warning for C. Because it looks scary, but we just talked about this compound. Yeah, so that would be methylammonium. right, since it has the 4 H's. And so is this acidic, basic, neutral for this salt? What do you remember about those ammonium salts? It's also a cation, so cations are always this one thing, or not.
No. Acidic?
Yeah, acidic, so right, it's acidic, so thinking back to our ammonia, ammonium combination, this, again, our methyl ammonium, so it's acidic from this, and then, right, our nitrate, exactly, so then nitrate, neutral, so overall, this is acidic. Then last one, nachos here. Do we recognize what this might be, or at least what group it might come from? Yeah, so it should look like acetate, except even simpler. So we'll look at our sodium. And so what that is this little guy, right? CHO2. And so this is from formate, or formic acid. But yes, if you start seeing like a bunch of carbons and 2 oxygens on it, a good guess for these type of problems is it probably came from some organic acid. Yeah, what's neutral? So then that makes formate, so it's negative. Yeah, a base. So then formate is a base. Yes. And then we won't, like I said, we won't worry about these cases of having to compare the Ka and the Kb strength. All right, we're kind of a little over time. So this means Monday we'll probably do some more of this math. A quick overview. So this is just kind of what we're going to be doing, some titrating. So notice if you have a strong acid versus a strong base titration, that goes from a low pH to a high pH. Notice your equivalence point. And so if we were to do a weak acid versus a strong base titration, you have, again, your equivalence point. It's a little different, so it's not quite on 7. And then, of course, once you blow past the equivalence point, it just turns into a base. If you have a polyprotic acid, then you have to account for the equivalence of protons. So again, I'll help you guys once we migrate to lab.
Quick question. Is next week week 8, or am I just counting weeks wrong?
Next week is week 8 and the last week, so we have review on Monday, final Wednesday.
Oh, okay.
Yeah, double final Wednesday.
Yeah, double final Wednesday.
Oh, God.
And so these are some indicators. Thymal blue is pretty popular. So notice thymal blue has 2 points. So 2 indication range. So you have really acidic, then kind of this middle range of yellow, and then a green equivalence point, then back to blue. So that's nice. We'll be using phenolphthalein today. So this is commonly used. So it's an acid-base indicator. And yeah, so we'll stop here. We'll finish the math on this chapter on Monday and / in lab, but I will give you all a 10-minute break and see you in 10 minutes.